Recording started.
All right, so this is going to be the recording, first recording anyways, to help us prepare for the final exam. And I'll just kind of ask you some questions along the way. These will be questions in purple. So first we're going to talk about the law of conservation of mass. So mass is kind of like weight, right? And so basically it says that matter can neither be created nor destroyed in a chemical reaction. Okay? So when it says that we're conserving mass, it basically means that mass or matter is not lost in a chemical reaction. And it basically means that the amount of matter or the amount of mass on both sides of the chemical equation are the same. And you can see that here because if you start with 12 grams of carbon and 32 grams of oxygen, 12 and 32 add up to 44. Okay, so you can see that in this reaction nothing's lost. There's no matter or mass lost, right? So if you look at the red text here, you can see we have the same number of each atom on both sides, okay, because we have one carbon, two oxygens and two oxygens, right? And we have the same amount of matter as well, because we have 44 grams on the left side and 44 on the right, okay? So again, remember the law of conservation of matter says that matter is not created or destroyed, it only gets rearranged. Okay? So here's just kind of a cartoon that's showing that, and this guy, you know, does 70 kilograms in his reaction here, and you can see he makes a bit of a mess here, but no matter what the deal, he still ends up with 70 kilograms, right? So it just says no matter how big the bang, matter is neither gained nor lost. Okay, so could you kind of tell me, Julianne, what does the law of conservation of matter state? Could you just kind of say in your own words again what it's about? Okay, well, remember, we're talking about the fact that matter is not created or destroyed, it only gets rearranged, right? Okay, so basically it's saying that we have the same thing, amount of mass that we start with, that we end up with, okay? All right, so let's try really hard for the next question, all right? For the next one's coming up. So there was a guy named John Dalton, and he believed that all matter was made up of small particles called atoms. So he came up with the theory of the atom that we hold to today. Okay, so here's kind of a picture of the atom. And so remember then, with the atom, we have the protons and neutrons in the middle of the atom. That makes up the nucleus. And we have this little speedy electron that just kind of zips around. And remember that the protons have a positive charge. Just think proton starts with P. And the electron has a negative charge. Okay? And the neutron has no charge. So, sorry, I'll just wait till the phone stops ringing there. I should have taken the phone away. Anyways, so remember this, that atoms gain electrons. When they gain electrons, they end up with a negative charge. And that makes sense, right? Because remember, electrons have a negative charge. So the more electrons you get, the more negative your atom becomes. And so it becomes an ion, right? Because normally atoms have no charge, but if they get a charge, they become an ion, right? Okay, so if an atom gains electrons, it becomes a negatively charged ion. If it loses electrons, it gets a positive charge. Okay? So an anion is an ion with a negative charge, and a cation is an ion with a positive charge. Okay? So there's something on the next page that will help you remember that. Do you like cats, Julianne? Okay, I'm kind of more a dog lover myself. But let's say, pretend we like cats. So if we say that cations are positive because cats are positive, right, that can help us remember that positively charged ions are cations and negative ions are anions. And if you think of the anion, it kind of sounds like an onion. That's a way to remember it as well. If you think onions are smelly, then that's negative as well. Okay? So that's how to remember the difference between anions and cations. Okay, so question. Do you remember what Dalton said all matter is made up of? What do we call those little particles? That's right, atoms, good. And how about number 3? What's a positively charged particle called? Okay, good. Great stuff. Let's go to the next stuff then. We're talking about isotopes at this point. Okay, so what are isotopes? Isotopes are atoms that have different numbers of neutrons. Okay, so these two atoms are called isotopes of one another. Okay, so you can see the two elements have different number of neutrons. So basically the red balls stand for the number of protons or electrons, okay, because the number of protons is always the same as the number of electrons. The gray balls here stand for the number of neutrons. Okay, so you can see here we have 6 is the atomic number. That means the number of protons is 6, and the number of electrons is also 6. But here you can see there's 6 gray balls, so that's 6 neutrons, whereas here there's 8, so here there's going to be 8 neutrons. Okay, so the number of neutrons is different with isotopes. That's the key difference, okay? So remember, the number of protons or electrons is the same for isotopes, but the number of neutrons is different. So, since it's the number of electrons in an atom that determine its chemical properties, do you think that two isotopes will be similar chemically, or do you think they'll be different if they both have the same number of electrons? That's right. Since the electrons determine chemical properties, if they have the same number of electrons, they're going to be similar. Good stuff. So I just wrote down here, two isotopes have the same number of protons or electrons, so they are the same chemically. Because again, it's the electrons that make the difference in atoms, how they react with other atoms, okay, in a chemical reaction. It's only their number of neutrons that makes them different. Great stuff. Okay, so we got a picture of a bike here, and the reason for that is we're talking about binary compounds, okay? So the reason the bicycle is called a bicycle is because it has 2 wheels, right? Bi equals 2. So let's look at an example of a binary compound. NaCl is a binary compound because it's got 2 elements joining together, right? Sodium and chlorine, okay? So let's look at the next 2 questions then. Question number 4. 2 isotopes are different in their, what would you write in here? So what's different about 2 isotopes and what's similar? Okay, they're similar with the number of protons. So that's what we would write for protons. Do you remember what else they're similar in? If they have the same number of protons or positive charges, they'll also have the same number of what? You remember with an atom, the positive and negative charges equal out. So if they have the same number of protons, they'll also have the same number of what particle? Protons are positive. Which are the negatively charged particles in atoms? Okay, those are the electrons, right? And remember, it's the electrons that give them their chemical reactivity, how they react with other atoms, right? Okay, so two isotopes are going to be similar in their chemical properties, right? If they're similar in electrical, their number of electrons, rather. Okay, now what makes two isotopes different from one another? Which particle? Okay, well, this one is the neutrons, right? Okay, so they have different amounts of neutrons, but the same amount of protons, electrons, and chemical reactivity. Okay, now, can you tell me what two binary compounds are? Or what a binary compound is, I should say? Okay, and what does the word bi mean again? Just think of the word bicycle. What number is suggested by the word bi? Yep, and so with a binary compound, it's always two elements joined together. Good. All right, so let's kind of shift gears and let's look at acids and bases right now. And I wrote here, acids are red, bases are blue. It kind of sounds a little bit similar to the poem, you know, roses are red, violets are blue. That's just to get the idea here that a base will always turn litmus blue. Okay, so litmus is kind of a paper that you can use to test if a substance is an acid or a base. Okay, so if it's a base, it's going to turn blue, and that's really easy to remember, right? Because base starts with B and blue starts with B, right? So once you remember that base is blue, then you know that automatically acid is going to be the other color, which is going to be red. Okay, so basically what this is showing us here is red litmus paper put into some base. And because it's turned into base, you can see it turns blue. And that makes sense because base equals blue, right? Now, we know that acids are red, or at least they turn litmus paper red. And so because this was a blue litmus paper originally, it was put in acid. And that's why it's turned red, right? Okay, so that's not too bad, right? So now we're going to kind of shift gears and look at solubility. So you remember what a solution is. Basically, a solution is formed when one substance dissolves into another substance. So for instance, if you take a bunch of salt or you take a bunch of sugar and you put it in water, it's dissolved in water and that forms a solution, right? So because it dissolves in the water, we call salt or we call sugar a soluble solid. Okay, so a soluble solid is a solid that's able to dissolve into something else, like water. Okay, so we say salt is soluble in water. Now let's look at something different. If we look at rocks, rocks are not soluble in water, right? So we say that they're insoluble. Excuse me. So there's another special word. When you have a chemical reaction, sometimes you have this kind of solid formed, right? And this solid will not dissolve in the rest of the solution. And we call this special solid a precipitate. Okay, so an insoluble solid that's formed in a chemical reaction is called a precipitate. All right? So that's a precipitate. Let's see if we can answer these questions then. So what color do you think blue litmus is going to turn if you put it in HCl? Remember, HCl is hydrochloric acid. It's that acid that's inside your stomach. It eats away at the food that's in your stomach. So what color do you think the blue litmus will turn? That's right, blue litmus is going to turn red with an acid. So how about question 7? An insoluble solid formed in a reaction is called a, do you remember what that word is? I know it might, I'm not sure if you'll remember how to spell it. Do you remember what letter it starts with? And if you do spell it, I can remember how to spell it, that's great. Okay, it actually starts with P. It's precipitate, right? Remember, whenever you're talking about snow or rain, that's precipitation. Okay, so that's kind of a similar word. Okay, so an insoluble solid is a precipitate. All right, so at this point we're going to look at the difference between a bare bones chemical reaction and a balanced chemical reaction. So basically a bare bones chemical reaction is like this one. And all it shows you is the different chemicals that are reacting together. It's not showing you a balanced chemical reaction. Okay, so here you have 8 sulfurs, and here you only have 1. So this next one here is a balanced chemical reaction, because here you see you have 8 sulfurs, and you have an 8 in front of the S, so that means you have 8 sulfurs as well. If you look at the number of oxygens, you have O2, which means 2 oxygens, multiplied by the 8 in front. 2 times 8 is 16. And here you have 2 oxygens. And again, because the 8 is in front of both the S and the O, you're going to have 8 times 2, which is 16 oxygens. Okay? So you have 8 S's, or sulfurs, on both sides. You have 16 O's on both sides. So because all the atoms are balanced, this one's a balanced chemical equation. Okay? So I just wrote here, what does a balanced chemical equation have that a bare bone equation does not have? In other words, what makes it balanced? And basically that's the same number of elements on both sides. Same number of atoms, I should say. So let's kind of shift gears here. We're going to look at formation and decomposition reactions. Okay, so just like the name suggests, when you have a formation reaction, something new is formed, right? So you had sodium and chlorine, and they joined together to produce a new product, which is sodium chloride, which is just good old table salt, right? Okay, so we have a new product formed with the formation reaction. A decomposition reaction is kind of the opposite. You know, the word decompose basically means break down, right? You know, when you talk about decomposers that are little creatures, we're talking about things like bacteria or worms or things like that, right? And what do? They break things down into more simple things, right? So we're breaking this compound down into the more simple elements that make it up, okay? So that's a decomposition reaction. So I just wrote here, what's the difference between a bare bones equation and a balanced equation? What would you say for that? Okay, so for a balanced chemical equation, what's the same on both sides? You have the same number of what on both sides? Okay, remember it's the same number of atoms, right? Because here you have 8 sulfur, here you have 8 sulfur, 16 oxygen, and 16 oxygen. Okay, so the same number of atoms on both sides. Now can you tell me what happens during a formation reaction? What does the word formation suggest? Okay, well, a formation reaction, we see that something new is formed, right? Decomposition reaction decomposes or breaks down. Okay, let's see if you can get the next questions. I bet you can. So acids and bases, they neutralize each other, right? They cancel each other out during a neutralization reaction. Okay, how do they cancel each other out? Well, an acid has a low pH, a base has a high pH. And what do you end up with? You end up with something in between, which is a neutral pH, okay, when they react together. So you can see why a neutralization reaction is called that. It produces a neutral pH. And neutral just means like zero, it just means neither acidic nor basic. It's just kind of neutral, right? It's actually a pH of 7. Okay, so here's kind of a picture of that. You have an acid which has a really low pH, a base which is a really high pH, and when they react together you get a neutral pH of 7. Okay, so can you tell me in some general terms, just kind of describe what takes place during a neutralization reaction? Okay, can you put it in other words? Usually it's best when you're coming up with a definition to think of some other words that are a little bit different than the actual word you're defining. So think of some other words to describe what is actually taking place. Okay, well the picture shows us, right? Okay, so the picture shows us basically an acid and a base are combining together and canceling each other out. Okay, what we're going to look at now is how to find the molar mass of a substance. So the molar mass means the mass of 1 mole of a substance. Okay, so we would need to look in our periodic table. So for instance, what's the molar mass of carbon dioxide? That's the mass of 1 mole of carbon dioxide. So what we would do is we would look in our periodic table and we would look at carbon is 12 in our periodic table. So you look at the beginning of your textbook. Okay, so carbon is 12, oxygen is 16, but there's 2 of them. So we need to multiply 16 times 2. That gives us 32. We add that together with the 12, which is carbon. 2 and 32 gives us 44. Okay, I'm gonna do the next one for us as well. And maybe I'll just kind of ask you a few of these purple questions as we go along, because we want to be able to finish on time. So if we have C2H6, what's that going to be? Well, if you look in your periodic table, again, carbon is 12, so we multiply 2 times 12. Hydrogen is 1, so we multiply 2 times 1. Okay, and 2 times 12 is going to give us 24, and 2 times 1 is 2, so 24 plus 2 is going to give us 26, and that's going to be our mass. Okay. You might remember from last session we talked about kinetic energy, and again, kinetic energy, anything that moves has kinetic energy, and you can see that all these things move, and a snail is going to have less kinetic energy, of course, because it moves more slowly, but that's basically just kind of a refresher of what kinetic energy is. Also remember, this graph is showing us that the temperature is related to the average kinetic energy. Okay? Basically, average kinetic energy is a definition for temperature. So if we look at these questions here, temperature is related to the average, what kind of energy of the substance? That's going to be kinetic energy, right? Okay. Question 13, so an increase in temperature means that what is being added to the substance? Well, since temperature is related to kinetic energy, if we have more temperature, higher temperature, we have more kinetic energy. That's what would go in those blanks for question 13. Okay, so is that making sense? Okay. Is there anything you'd like to ask me about here? Okay. All right. Well, if you do think of a question, just let me know, okay? So we're going to keep moving then. So remember in the last session we talked about the difference between scalar quantities and vector quantities, and we said both scalar quantities and vector quantities are measurements, they have units, but only vector quantities involve direction, right? So for this question here, it says a race car is driving along a straight portion of the track and it moves from A to B, okay? And it says it moves in 0.95 seconds. It says, what is the best description of the average speed of the race car? So we need to remember what the formula is for speed, and we need to remember whether speed is scalar or vector. Okay? Now, you might remember from last day that speed is a scalar, okay? Because speed only has units, it doesn't have direction. So for speed, you're going to be talking about something like 100 kilometers per hour. Right? So if you look on the sign on the side of the road, that's going to be speed. Okay? So the formula is distance over time. So if we look at this question then, sorry, I just have to find my calculator. Okay. We look at what the distance is. I know it's not very easy to see here. It might be a little better if you look on the file here. But you can see the distance, there's one distance that's added to the other distance. 32.5 is added to 11.7. And so that's going to be 44.2. Okay, so it's 44.2 meters divided by, how much time is it in the question? You can see it's 0.95 seconds, right? Okay, so we would divide 44.2 divided by 0.95, and that's going to be 46.5. Okay, so 46.5 meters per second, or about 47 meters per second. So for this question, it says, what's the best answer? Well, the best answer is going to be A, right? Because it's only meters per second, because since we're talking about speed, and speed is scalar, and scalar does not involve any direction, it's going to be answer A, okay? For the next one, though, the next one says, what is not an acceptable way to describe the velocity of the race car as it goes from A to B? Okay, so because it's velocity, it's going to be scalar, or a vector, sorry, and vector means that it has direction. Okay, so it has to have direction. So which one is not acceptable? In this case, A is not acceptable because 47 meters per second, or sorry, D is not acceptable because D just says 47 meters per second. It doesn't give us any direction. Whereas plus 47 meters per second, that gives us a direction, the plus does, right? 47 meters per second to the right gives us direction, and also 47 meters per second east also gives us direction, right? Okay, so again, if it's speed, you don't need any direction because it's scalar. If it's velocity, you do need direction, and that's why answer D is not correct. Okay, so does that kind of make sense? Okay, good stuff. So we'll go on to the next one, question 16. So this one here, it's a velocity versus time graph, right? And let's just kind of think about some differences with velocity, the different kind of speeds we can have, different ways that objects can travel. So the first thing here says, for point 1, it says if we have a constant velocity, like a car traveling down a highway at 100 kilometers per hour, then the velocity stays the same, right? The number is always the same. It's always 100 kilometers per hour if it's a constant velocity, right? Now, if we have constant acceleration, remember if you're passing someone on the highway, then the velocity is going up and up, right? It doesn't stay the same. The numbers are going to go up and up. So, just a second. I'm going to be right back in just a sec. Give me a sec. Okay, sorry about that. So I just wrote down some questions here to think about it. The first one says, how would you describe the velocity of the object on the graph? Okay, so if you look at velocity, you can see the numbers are going up, right? They're not going to be the same. If they were going to be the same, then it would be a flat line, right? But because they're going upwards, the velocity is going up. So because the velocity is going up, if we look at the different possibilities for what word describes what's happening on the graph, it's going to be acceleration, right? If it was velocity, it would be a flat line because the numbers are always the same. But because the velocity is going up and up, that's acceleration. Okay? And again, please stop me if there's anything you could ask for help with. Okay? Okay. So we're going to talk at this point about what efficiency means. And so the formula for percent efficiency means input energy divided by output energy times 100. So what if we knew that a light bulb was 25% efficient at changing electrical energy into light energy? So what this 25% efficient really means is 25% efficient at changing input energy into output energy. Okay? So I've just kind of drawn this on the diagram. So here's the electrical energy you start with. That's 100 joules. You've produced 25 joules of output energy. Okay? So again, we divide the 25 by the 100, multiply by 100, and that gives us 25%. That's the formula for percent efficiency, this one here. Okay? So again, when we're talking about efficiency, that's how efficient are we at changing the original input energy into the output energy. Okay? All right. So let's look at a situation that talks about efficiency. And so let's say we're talking about electric motors, and so they're somewhere between 50 and 90% efficient at changing electrical energy to useful energy. Okay, so what kind of useful energy do you get out of a motor? Well, it's going to be kinetic energy, right? Okay, so it's electric energy to kinetic energy. All right, so let's say that we have a particular motor and it's 73% efficient. Okay, so let's think about what that means. So what it means is, if we're looking at the different possible answers here, 73% efficient, does that mean 73% of the input energy is wasted? No. Does it mean 73% of the input energy is converted to heat? No, because heat is going to be wasted energy, right? Does it mean 73% of the input energy is converted to kinetic energy? Yes, it's going to be that, right? Because the kinetic energy is the useful energy. Okay? So, another way of thinking what 73% efficiency means, it means for every 100 joules of blank energy, well, that's the energy you started with. That's the electrical energy. Okay, so I'm just going to type that in. Electrical energy. You're going to get 73 joules of what kind of energy? That's going to be kinetic energy. Or another way of saying it is 73 joules of useful output energy. Okay? That's another way we could have said it. All right, so we've got a question here. For every 100 joules of input energy supplied to the motor, how much useful output energy do you think is produced? Any idea? Look at the percent efficiency. Okay, if it's 73% efficient, for every 100 joules of input energy, you're going to get 73 joules of useful output energy. Okay, next question. It says for every 100 joules of input energy, how much energy is wasted? Okay, so you're getting 73 joules useful energy. How much of that 100 joules do you think is wasted energy? If you got your calculator, you can figure it out. Okay, well the 100 is what you start with. You get 73 useful, so whatever's left over is not useful. So 100 minus 73 equals 27. Okay? And the last question here says, if 25 joules of input energy is supplied to the motor, about how much useful output energy is produced. Okay? So basically this time we have 25 joules instead of 100 joules, right? So if 100 joules produces 73 useful, then 25 joules, which is a quarter as much of 100, basically we're going to have to divide 73 by 4, right? 73 divided by 4 gives us 18.25. Okay, so 18.25 useful energy. All right. So, what do you think, Julianne? If you look at this question here, it's showing us some different types of light bulbs. It gives us different numbers for their efficiency, right? So if you look at the different numbers for these light bulbs for their efficiency, which light bulb do you think converts the most input energy into useful output energy? That's right. That one's got the highest efficiency, and that's just, efficiency is just another way of saying how good it is at changing input energy into output energy. Great stuff. Okay, so we'll go on to the next section here. So we're talking about why we need electron microscopes. Well, the first microscopes they started with were compound microscopes. You might have used one of those over the years, okay? And those are good at objects. They're good at looking at objects that aren't too small, but smaller objects like proteins require a lot more magnification, okay? So compound microscopes are just not good enough at magnifying objects. So you need electron microscopes that are more powerful magnifiers, all right? And with those, you're able to see things like proteins. Now, speaking of proteins, there's certain parts inside the cell that produce proteins, and those are called ribosomes. And I'm just showing a picture here of an object that can be seen with an electron microscope. And it looks pretty cool under an electron microscope, doesn't it? And electron microscopes were actually invented in Canada, so I think that's pretty cool as well. All right. So we have a few questions here. The first one says, what's the reason why compound microscopes are limited in usefulness and why electron microscopes were needed? And so basically that's because of the magnification, right? It gives you more magnification. Question 23 says, what kinds of cell features require electron microscopes to be seen? And that's things like proteins are not able to be seen on compound microscopes. And where are proteins made? They're made in the ribosome. Okay? All right. So we're going to be looking at this point about stem cells. Okay? So basically stem cells produce all other cells. So it's pretty cool, eh? All these other cells in your body are originally produced from stem cells. And stem cells are found in the bone marrow of the body. And sometimes they have to do what's called a stem cell transplant. They have to get stem cells from one person to another. And so they have to get them from the bone marrow. Okay? So here, do you know what kind of cells we would say then are used to produce all other cells? Okay, as the diagram shows, it's a stem cell, right? And they're produced in the bone marrow. All right. What I'm going to do at this point is I'm going to just play a little video for you. Okay? So I'll put that up on the screen. And sorry, I just have to quickly log into the school so I can get that link. It won't take too long. It's just a little quick, basically it's a guy singing. Okay, so Julianne, if you could just click on that and watch that, and just let me know when you're done, okay? Okay. All right. So let's see if you remember any of the terms from there. The ones I wrote in kind of darker words, more bold, are kind of the terms that were used by the guy as he was singing. So can you remember, when you look at any of these dark terms here, can you remember any of the names of the organelles, the cell parts that go with those descriptions? Okay, chloroplast stores sunlight, right? It takes sunlight and stores the sunlight's energy. Can you think of any others? That's good. The cell membrane is the gatekeeper. Good stuff. Right on. Okay, so the cell membrane controls what goes in and out of the cell. Anything else? Okay, the Golgi apparatus packages and sorts. Good stuff. Anything else? Okay, well maybe I'll just go over the next one. The energy factory, that was the mitochondrion. Changes glucose or sugar into usable energy. The lysosome dissolves in enzymes. It dissolves other things in enzymes. In other words, it digests them, and it's kind of like cellular recycling. The storage dude that he talks about in the song, that's the vacuole, okay, and that stores materials in the cell. Okay, and so here I was just wanting you can practice it over again on the PDF file, the same questions. Okay, so just a few more pages to go. Actually, first of all, would you like to get a drink or something? Let's take a bit of a break. Okay, all right, we'll keep rolling then. So we're going to talk at this point about the difference between weather, climate, and seasons. So weather is kind of like the temperature and precipitation. So precipitation, we mean like rain, snow, that we get on a daily basis, right? Changes from day to day. Climate is when we look at the average long-term weather, or the temperature or precipitation patterns in an area over the long term. Okay, so climate is the average weather. Now, what changes the climate and weather? What is it that leads to them? Well, it's things like air pressure systems. So sometimes weather people talk about high pressure systems, low pressure systems. It's also the latitude, right? You know, like how far north or south you are. And also how close you are to things like lakes, oceans, mountains, right? All those things affect the lakes, or sorry, affect the weather and climate. When you talk about the seasons are periods where we experience specific temperature or precipitation patterns, and they're caused by the tilt of the Earth. All right? And in a minute, we're going to look at one more video that has to do with that. So the tilt of the Earth causes seasons to occur, and you can see why it's warm in Canada during winter and cold, or yeah, I wish. during summer and cold in winter, right? Here's something that's interesting though. Do you know that we're actually closer to the sun in the winter than we are in the summer? That's kind of bizarre. Most people think, when they find that out, they think that's unusual, right? And again, it's because what actually causes the seasons is not how close we are to the sun, it's the tilt of the Earth, right? And how that affects how much sunlight we get. So I just got a question here. What's the definition for climate? Again, climate is the average weather we have over the long term. What causes the seasons? That's the tilt of the Earth, right? Okay, so before we go on to the next page, I'm going to give you another video to watch. And so, again, let me know when you're done this video. It'll take about 2 minutes in all. Okay, good stuff. So what did you think? Was that kind of cool? Yeah, I thought it was kind of cool. All right, so let's just finish up the next few pages then. We looked in the lessons about biomes that exist in Canada. And so a biome is just a large area of land where there's similarities in land forms, like the type of land is similar, so maybe the vegetation and that sort of thing. And also the climate is similar as well, right? So this is just showing the different biomes that are in the world. And you can see the ones like the rainforest, these green ones here, are found in the warmer parts of the world, so around the equator, right? And of course, rainforests are very warm and they also get a lot of rain. And on the other hand, the tundra, which is in the north of Canada and also Russia, it's kind of the opposite. There's small amounts of rain there, and it's very cold, right? And now the tundra is only found near the Arctic. It's not found near the Antarctic in the South Pole, okay? So just looking at the questions on the next page, what parts of the world are the rainforest and tundra biomes found? Found in, I should say. Rainforest is found around the equator, right? Tundra biomes, the north area, around the North Pole, close to the North Pole, not quite the North Pole, but the Arctic area, okay? So just below the Arctic Circle, around there. All right, let's look now at this point. We're going to talk about the different parts of the world where water goes to. Okay, so water's found, the area where water's found is the hydrosphere, because hydro often means water, right? So the hydrosphere is where it starts, then it evaporates up into the air, and the air is called the atmosphere, and then later it falls down as rain, and then when it absorbs into the land is the lithosphere. Okay, so remember all three of those parts, the hydrosphere, the atmosphere, and the lithosphere, are involved when we talk about the hydrologic cycle, and the hydrologic cycle is just a cycle that involves water. Okay? So now we're just going to look at water and carbon dioxide, how they're greenhouse gases. I don't know if you remember, we talked about the greenhouse effect. And basically the way the greenhouse effect works, like with a greenhouse, what happens is light energy gets through the glass of the greenhouse, then the light contacts different objects, strikes objects inside the greenhouse, and that changes the light waves into heat waves. Now heat waves are not able to pass back through the greenhouse. So because of that, well, hi Julianne, did you get kicked off for a sec there? Okay, that's too bad. So I was just explaining about what happens with the greenhouse effect, right? And so what happens with the greenhouse is you have light waves can pass through the greenhouse, right? Then they strike objects inside the greenhouse, and that changes the light waves into heat waves. Now heat waves are longer than light waves, so they're not able to pass back out of the greenhouse, and so that heat gets trapped inside the greenhouse, and that's why a greenhouse is hot, right? It's the same thing with our environment. That's why we call it the greenhouse effect, is these greenhouse gases, which are water and carbon dioxide. Okay, so even water can be a greenhouse gas. They act just like the light, or just like the glass of a greenhouse. Okay, so just like a greenhouse, the light is able to pass through our atmosphere, but once it's changed into heat waves that are longer waves, they're not able to pass back out of our atmosphere, and that's why over time some people think that the greenhouse effect could lead to global warming. Okay, so remember, it's things like carbon dioxide and even water that are the greenhouse gases. And so, you know, some people have concerns about too much carbon dioxide being produced by factories and cars and that sort of thing. And speaking of that, they say that the greenhouse gases produced by the transportation industry, so for instance trucks, you know, even though there's been a lot of stuff in the news about the greenhouse effect, those greenhouse gas emissions from trucks have not gone down over the years. They've stayed the same, or they've even gone up. Okay, so a few questions here. One is, name the three areas where water is distributed in the hydrologic cycle. Okay, that's going to be the water starts off in the hydrosphere, then it goes up into the atmosphere, and it also soaks down into the ground, which is the lithosphere. Okay? Question 30, name two types of substances that are greenhouse gases and play a part in the greenhouse effect. Okay, one is carbon dioxide, that's kind of the main greenhouse gas. The other one is water. And then question 31, explain the trend with greenhouse gas emissions in the transport industry. Basically, the emissions have not gone down, so they basically stay the same or even gone up. And that's looking like our last question. So again, please practice all these. We should do one more session as well before the final exam, but if you can practice these questions on this file here, that's going to help a lot for preparing for the final. So